The Mustang sat at the end of the runway with its nose pointed into a dirty English sky, propeller ticking over in that restless, uneven way Merlins have when they're waiting to be let off the leash. Dirt and gravel pinged off the underside of the wings as the wind gusted across the field. Ground crew and oil-stained parkas pulled chocks, stepped back, and watched the pilot in the cockpit bring his gloved hand up to the prop control. In most of the world's air forces, at the start of the 1930s, that control would have been an afterthought. A lever that changed the pitch of the blades once or twice on a flight, if at all. Something you set and forgot. Engines were what mattered. Horsepower was what mattered. Props were the loud, whirling discs on the front that turned fuel and noise into more or less forward. But in this Mustang on this morning, the propeller was the smartest thing on the airplane. The pilot pushed the throttle smoothly forward. The Merlin's note climbed, but the RPM needle stopped dead on a number and stayed there as if pinned. On the spinner, the 4 Hamilton Standard blades quietly twisted to a finer bite, taking smaller bites of air faster, letting the engine dig into its torque without overspeeding. The airplane moved. At first it was just a tremor through the wheels, the slow rolling start as weight overcame static friction. Then, as the blades kept trimming themselves to hold that perfect RPM, the trembling turned into a long, hard shove. The Mustang surged down the runway as if a hand had grabbed it by the nose and decided the ground was no longer where it belonged. The pilot felt it in the small of his back. This wasn't the old fixed pitch kind of acceleration, the noisy but lazy rush where you heard the engine scream and watched the world crawl. This was different, controlled, efficient, brutal. By the time he reached the halfway point of the strip, the aircraft was already light. A small pull on the stick and the main skipped. A heartbeat later, the wheels were clear. The prop coarsened automatically to hold the RPM exactly where the chart said maximum climb power lived, and the Mustang knifed upward into the clag, leaving little more than a spray of water and a fading echo behind it. Down on the ground, an older pilot watching the takeoff shook his head. Same engine? He asked the crew chief. Same engine? The crew chief said, different genius on the front. The genius on the front wasn't the pilot. It wasn't the Merlin. It was the propeller and the engineer who had insisted for years that propellers could be clever. His name was Frank Walker Caldwell. If you'd met Caldwell in 1918 at McCook Field, you wouldn't have guessed he'd be the one to tilt the sky in the Allies' favor a quarter of a century later. He didn't look like a man who shaped battles. He looked like a man who kept notebooks, which he did cramped lines of numbers, angles, RPM values, thrust coefficients. While others wrote memoirs, Caldwell wrote test plans. By the end of the First World War, he was already something unusual, an engineer whose entire job was propellers. At McCook and later Wright Field, he took over the propeller research department, designing whirl rigs that mounted propellers on stands and spun them under controlled conditions, measuring thrust, efficiency, structural strength. It sounds dull. It wasn't. Every revolution on those test stands was a small argument with the air, an argument Caldwell intended to win. Wood became metal. Fixed pitch became adjustable. Pilots learned to pull a lever and change their prop from fine to coarse in flight, like shifting from first to third in a truck. Airlines noticed, so did the U.S. Army. When Hamilton Standard's hydraulic two-position controllable pitch propeller went on Boeing's shiny new Model 247, and suddenly crossing the Rockies became routine instead of a nail-biter, the industry understood something had changed. The Collier Trophy, the biggest public well done in American aviation, went to Hamilton Standard in 1933, with particular credit to Frank Caldwell, chief engineer for development of a controllable pitch propeller. That would have been enough for most careers. Caldwell treated it as a warm-up too. Position props were better than fixed pitch, but they were still clumsy, fine for takeoff, coarse for cruise, and nothing in between. In the real sky, with gusts and climbs and dives and load changes, engines live everywhere in between. Caldwell kept looking at his graphs and seeing the waste. Pilots either let the engine overspeed in a dive, beating itself to death for no gain, or they throttled back to keep the RPM in check, throwing away potential energy. In climbs, a coarse pitch meant the engine lugged working harder than it needed to for less climb. He wanted something no one had yet built in a reliable form, propeller that could change its pitch continuously, automatically, so that the engine stayed at its best RPM no matter what the airplane was doing. Constant speed, not a marketing phrase, a control law. He wasn't the first to think of it. British and German engineers had sketched similar schemes. What made Caldwell's version different was that it worked reliably under combat conditions, on engines that shook and leaked oil and were handled by rushed line mechanics in bad weather. On paper, the principle was simple. Propeller is an air screw. For any given engine and airframe, there's an RPM where the engine develops its best power, and the propeller converts that power into thrust most efficiently. If you could hold that RPM steady and let the blade angle vary to meet whatever the sky threw at you, you'd always be as close as possible to maximum performance. The stumbling block was making the blades move themselves without asking pilots to babysit another lever. Caldwell solved it by adding one more piece of clockwork to the system, a governor. He teamed up with the Woodward Governor Company in Rockford, Illinois, experts in mechanical governors for industrial engines. Together they built a compact device that used centrifugal force, spinning weights on a shaft responding to RPM, to move a hydraulic valve. The faster the engine spun, the more the flyweights flung outward. The valve opened or closed, sending pressurized oil into a piston in the propeller hub, twisting the blades toward coarse or fine pitch as needed. If the RPM rose above the set point, the governor increased blade pitch, making each blade take a bigger bite of air, loading the engine and slowing it. If the RPM fell, the governor flattened the blades, reducing load and then letting the engine speed up again. The pilot no longer had to think about it. He picked an RPM with the prop lever. The system did the rest. Airline brochures called it the automatic gear shift of the air. Engineers called it a constant speed propeller. Mechanics' notes called it one more damn thing full of oil. But pilots, once they'd flown behind it, had another word: miracle. Late in 1935, Hamilton Standard put the first of these constant speed units into production. Airliners like the DC-2 and DC-3, Boeing 247s, Clippers and transports from Sikorsky and Lockheed began to take off with a new sound, a steadier tone, a hum that didn't rise into a frantic scream on climb-out because the RPMs stayed put while the blade angle did the work. By 1939, Hamilton Standard had already sold tens of thousands of them. Within a few years, almost every significant U.S. military aircraft would be spinning Caldwell's idea on its nose. But how much difference can a propeller really make? To answer that, you have to sit in two airplanes that look the same from the outside and feel utterly different once they move. The first is an early fighter with a fixed pitch prop. You line up on the runway, throttle forward. The engine roars past its rated RPM, almost immediately the needle flirting with the red line. Tie down chains rattle somewhere in your memory because you've seen what happens when an engine overspeeds on test. Valves floating, pistons outrunning their balance, connecting rods trying to exit the block. You pull the throttle back a little to spare the engine. The airplane lumbers forward. Takeoff roll stretches longer than you like. Obstacles at the far end of the strip look a little closer than they should. When you finally lift off, the climb is shallow. You feel every pound of fuel and ammunition as reluctance. At altitude, in cruise, the propeller is now turning too slowly for best efficiency. You're dragging it through the air like a poorly chosen gear. Now you step into the same airframe with Caldwell's constant speed propeller bolted on. Same engine, same weight, same pilot. Throttle forward. The RPM rises and then locks like a soldier coming to attention. The governor begins trimming the blades constantly, tiny hydraulic adjustments smoothing out the dance between engine and prop. You feel the difference in your spine before you see it on the altimeter. The acceleration pins you harder against the seat. The airplane lifts off earlier. When you pitch up into climb attitude, the engine doesn't bog down. The governor simply eases the pitch finer to let it spin where it wants, keeping power up. Instead of watching the RPM gauge with dread, you barely glance at it. It's boring now. It just sits at the number you chose. Down below, the runway goes by in fewer seconds. Up above the altimeter, needle moves faster. On the climb chart, the line for constant speed propeller sits well above the line for fixed pitch all the way to altitude. When Caldwell and his colleagues ran these tests for real at Wright Field, they weren't imagining the difference. It was there in black and whitey, shorter takeoff runs, faster climbs, higher ceilings. The same engine, treated better and asked to work where it was strongest, gave more without burning more fuel. Now plug that difference into wartime. Picture a B-17 heavy bomber in England, winter of 1943. The field is half mud, half frozen ruts. Each flying fortress is loaded deep with bombs and fuel. The strip is barely long enough on a good day. On a bad one, with overcast at a few 100 feet and crosswinds, it feels like an accusation. With fixed pitch props, you'd need perfect technique and a little luck. Too much throttle, and you'd overspeed the engines, risk damage before the mission even started. Too little and you'd never reach takeoff speed in time. Engine management would fight you every second of the roll. With constant speed props, the pilots could confidently push to takeoff power. The governors would hold RPM where the engines were rated. The blades, in fine pitch, would grab the air and hurl it backward as efficiently as possible. The result was measurable bombers came off the ground hundreds of feet earlier than their fixed pitch cousins. Climb rate improved. Formation assembly time shrank. Fuel burn stabilized. A formation that would once have wallowed low and vulnerable in the flak belt could now punch up through to its escort altitudes with more margin. In fighters, the effect was even more visceral. The P-47 Thunderbolt, the Jug, was a monster of an airplane, 10,000 pounds of R-2800 engine wrapped in armor and fuel. Early in its service, German pilots laughed at its climb rate. It dove like a safe and hit like a hammer, but it seemed to go uphill like a truck in sand. Then Hamilton Standard hung a new set of big paddle blade, constant speed props on its nose, blades that could absorb the full output of that double wasp and convert it efficiently. Climb rates jumped by hundreds of feet per minute. Top speeds edged up toward 470 mph. German laughter stopped. The principle was the same on everything from Wildcats to Lightnings. Give the engine a prop that can keep it at peak RPM while changing blade angle to match the load, and suddenly an airplane that felt merely adequate feels like it's been reborn. And then came the P-51. Early Mustangs with Allison engines were good low-altitude fighters, but left something on the table up high. The British bolted a Rolls-Royce Merlin into the airframe and transformed its high-altitude performance, but it was Caldwell's constant speed propeller on the nose that made sure every one of those supercharged arched horsepower units was actually doing useful work. A P-51 with its 4-blade Hamilton Standard hydromatic prop turning at 3,000 RPM in climb could shoot from sea level to combat altitude in minutes less than a similar airframe handicapped by cruder propeller technology. Operational ceilings went up by thousands of feet because the propeller could keep pulling efficiently even as the air thinned, automatically coarsening its pitch to extract what it could from the thin air without letting the RPM droop. Climb first, then faster, then higher. That sequence, more than any marketing slogan, was the meaning of Caldwell's impossible propeller. The impossible part came not from physics, it came from culture. In the late 1920s and early 1930s, A lot of experienced aviators looked at Caldwell's early hydraulic props and said, too complex, too many things to go wrong. We need simple, not clever. From one perspective, they were right. Early variable pitch systems had been heavy, unreliable, or both. Anything that depended on moving parts inside a spinning hub, actuated by fluid and springs and tiny valves, looked like something that would fail at the worst possible moment. Caldwell's answer was to over-test it. On the whirl stands he designed, he ran propellers to destruction, monitoring not just thrust and efficiency, but how oil seals wore, how piston rings fared, how fast governors responded when the load changed suddenly. He threw simulated gusts at them, cranking the dynamometer load up and down rapidly to mimic dives and pull-outs. He subjected them to temperature cycles and contamination because he knew field oil was never as clean as lab oil. Then he looked at maintenance logs, a constant speed prop that failed once every 10 flights would be a disaster. One that failed once every few thousand hours would become invisible to crews. Just another system that always works. By the late 1930s, Caldwell and Hamilton Standard had the failure rate where it needed to be, low enough that the pilots stopped seeing the propeller as an experiment and started seeing it as a given, like wings. That's when he added something else of feathering. If an engine failed on a multi-engine aircraft with a fixed prop, the dead engine's propeller would keep windmilling and creating massive drag. It was like throwing out a barn door in the slipstream. You could lose tens of knots of airspeed fighting that drag, and in marginal conditions, that could be the difference between limping home and falling short. Caldwell's hydromatic constant speed props could twist their blades all the way to feather, edge onto the wind when an engine quit. The same hydraulic system and governor logic that kept RPM constant in normal operation could, on command, drive the blades to 90 degrees, reducing drag to almost nothing. Pilots in B-17s, B-24s, and later B-29s who lost an engine over hostile territory learned to love that feature. Number 3 just quit, the flight engineer would say. The pilot would call feather 3. A lever went forward, a warning light blinked. The dead engine's prop slowed, then stopped, blades narrowing into the wind. The bomber yawed slightly, then steadied. Airspeed stayed safely above stall. They went home on 3, sometimes on 2, rarely, miraculously on 1. Feathering was dramatic. Constant speed was subtle. Both lived in the same Caldwell hub. By the time the United States entered World War II, Caldwell's hydromatic constant speed propeller was everywhere. DC-3S B-17s, B-24s, B-25As, P-39s, P-40s, P-47s, P-55E-1s, and countless trainers and transports spun them. Almost every USAAF aircraft of consequence had a Hamilton Standard on its nose or wings, quietly metering blade pitch to keep RPM where it belonged. This uniformity mattered. It simplified training. A cadet who learned to handle a constant speed prop on an AT-6 Texan could step into a fighter or bomber and find the same logic. Set RPM with the prop lever, set power with the throttle, let the governor do the rest. In the ready rooms, instructors drew simple diagrams on chalkboards to explain what the students would feel. Think of your propeller like the gearbox in a truck, one would say, chalk scritching across slate, but better. In a truck, you pick gears by hand, you can get it wrong, you can lug the engine or overspeed it. With this, he'd sketch a prop, a governor, arrows showing oil flow. You pick the engine speed you want. The propeller changes its own gear ratio to match. Climb, cruise, dive, it doesn't matter. The engine stays where it's happy. You keep your eyes outside, not on the tachometer. That was the essence of Caldwell's philosophy. Take work off the pilot's plate and put it into metal and oil. The tactical consequences showed up in places Caldwell never visited. North Africa, a dusty strip carved out of hardpan, sun beaten down like artillery fire, P-40s and P-39s parked wingtip to wingtip, sandbags and oil drums marking the edges. German bombers are reported inbound. The scramble alarm howls. Pilots sprint. Starters whine. Engines cough, then catch dust. Whips under spinning props with fixed pitch props. They'd have to compromise. Either baby the engines off the line, worrying about overspeed and risk being too low when the enemy arrived, or ram the throttles and trust to luck with constant speed props. They shove the throttles forward. Here the engines rise to the target RPM and stop, and feel the airplane surge. The runway is short. It doesn't matter as much as it used to. Takeoff distance is slashed, especially at high weight and in hot air. They're airborne sooner. They begin climbing sooner. By the time the German bombers arrive, the American fighters are not at treetop height trying to claw their way up. They're already at an intercept altitude, rolling in from advantage. In the Pacific, the same story plays out on coral strips barely wider than a city street. F-4Us and P-30As loaded with fuel for long over water missions roll with confidence because the propellers will give them every foot of thrust their engines can buy. On return, damaged and limping, they know they can set a lower RPM, nurse their engines, and still keep enough power to stay aloft. Constant speed props didn't just add speed, they multiplied options. They allowed designers to push aircraft into performance envelopes that would have been suicidal with older technology. High-powered engines with massive superchargers could be used safely throughout their range because the propeller could absorb their power without stalling the blades or overspeeding the crankshaft. They allowed operations from shorter, rougher fields. A fighter that needed 3,000 feet of runway for takeoff with a crude prop might only need 2,000 with a constant speed unit. Especially in heat and humidity, they allowed higher interceptions. Climb performance charts shifted. AP-51 could now be tasked to met enemy bombers higher and earlier, not wait for them to descend into its performance band. They allowed new tactics. Think about boom and zoom. A fighter pilot attacks from above, diving on an enemy, firing a burst, then pulling up into a climb to trade speed back into altitude. In an aircraft without a constant speed prop, this maneuver is a compromise. dive too steeply and the engine overspeeds, forcing you to throttle back just when you'd like all the acceleration you can get, pull up too sharply and the engine bogs at low RPM, delivering less climb just when you most need to get out of harm's way. With Caldwell's governor, the pilot can ignore the tachometer. The RPM stays nailed. In the dive, the prop coarsens, turning speed into thrust. In the pull up, it finds letting the engine accelerate even as gravity fights it. The airplane feels like a ball on a string. You slam it downward, you whip it back up, and the string never goes slack. Energy fighting, the art of converting altitude to speed and back again while keeping more total energy than your opponent, became more productive because Caldwell's props removed a major source of waste from the equation. Over Europe, in the cruel calculus of high-altitude escort work that meant Mustangs could linger above bomber formations, drop into the fight, climb back out, then do it again, all on a single tank of fuel. Over the Pacific, it meant Corsairs could tangle with Zeros using hit and run tactics and trust their engines to give them the same pull in the vertical over and over. Caldwell never shot down a German or Japanese aircraft, but there are pilots who did at 25,000 feet who could have traced a line from their gun camera film back through their engine mounts to a propeller hub, and from there, through patent drawings and test reports, to a man in a lab coat staring at a whirling blur on a stand and jotting numbers in a notebook. In 1934, Franklin Roosevelt shook Frank Caldwell's hand in the Oval Office and congratulated him on his propeller. The president spoke of a new horizon of aeronautics and proclaimed that Caldwell's work had taken the limits off speed. It was a politician's line, hyperbolic, but not wrong. By the mid-1940s, the limits on speed and climb for propeller-driven aircraft were no longer at the propeller. The limiting factors had shifted to aerodynamics, compressibility, and ultimately to the physics that would give birth to the jet age. Caldwell's hydromatic constant speed propeller had done something subtle but profound. It had completed the propeller's evolution. From there on, improvements would be incremental: better blade shapes, lighter metals, refined governors. But the core idea was done. A prop that thought for itself and let the engine play its full tune. When the American Society of Mechanical Engineers declared the hydromatic propeller an international historic mechanical engineering landmark decades later, they weren't just honoring a clever piece of hardware. They were recognizing a hinge point. The moment propellers stopped being slightly smarter windmills and became full partners in power plants. Frank retired from United Aircraft's research division in the 1950s. He'd spent more than 3 decades around propellers, designing them, testing them, arguing for them in conference rooms, listening to pilots talk about what they felt through the stick and seat. He died in 1974, decades after jets had taken over the glamour roles, after afterburners and swept wings had stolen the headlines. But in museums and on airshow ramps, whenever P-51 cranks its Merlin and taxis out, Something of Caldwell's invisible hand is still doing its work. The pilot sets the prop control forward for takeoff. The governor wakes up. Oil pressure stands ready. The blades are already adjusting themselves before the brakes are fully released. Throttle forward, RPM up, hold. The Mustang lunges, he rotates, he climbs. In minutes he is at an altitude where 80 years ago men fought for their lives in machines made better by an engineer whose name they might never have known. Climb first, then faster, then higher, and when you're the one who climbs first, you're the one who decides what happens next. One engineer's impossible propeller turned into free performance for U.S. fighters and bombers. It cut P-51 climb to altitude by minutes and added thousands of feet of ceiling. It turned short, muddy strips into launch pads and far, thin air into hunting grounds. It didn't just add speed, it multiplied options. Frank never flew combat, but his propellers helped decide where and when thousands of fights began. And in air combat, that's often the same as deciding how they end. Subscribe for more untold stories of World War II.